Hi, if you've ever taken a quantum mechanics class, or even just peeked into a textbook, you know how quickly the math can pile up, leaving you wondering, what's the subject really about? That's where this series comes in. In this series, I won't just throw formulas at you. Instead, I'll break down the postulates of quantum mechanics into clear, visual ideas with pictures, animations, and explanations that you can actually see. By the end, you'll have the big picture framework you need to finally make sense of what quantum mechanics is saying. This is video 2, where we'll dive into postulates 2 and 3. If you haven't seen video 1 yet, you might want to check it out at some point since it sets the stage, but you'll still be fine starting here. And if you're enjoying this journey, don't forget to hit like, leave a comment, and subscribe. Now let's move on to postulates 2 and 3. These two go hand in hand, so I'll cover them together. I'll put each postulate on the screen, one at a time, and read it out exactly as it appears in the classic Cohen Tannoudji textbook. The language is very dense, and for most people, it won't make sense right away. It's too formal and technical. That's why I'll spend the rest of this video breaking them down into clear, simple terms with animations explaining what they really mean. Postulate 2, the observable postulate. Every measurable physical quantity, script A, is described by an operator A acting in V, where V is a vector space. The operator is an observable, and then there's a comment in the textbook. Observables are Hermitian operators. Their eigenvalues are the possible measurement results, and their eigenvectors form a basis for the state space. Postulate 3, the measurement and probability postulate. When an observable A is measured, the possible result is an eigenvalue A sub n. If the system is in a normalized state psi, the probability of obtaining A sub n is given by this equation. And then there's also this side note for the probability density when you're dealing with the continuous spectrum. Now it's time to take the next step and explain in my own more intuitive, less formal and general way what the second and third postulates actually mean. We learned in video 1 that the state of a quantum particle is described by its wave function, psi of x. Postulates 2 and 3 will teach us that once we know the wave function, we can extract measurable information about the system. One of the most important pieces of information you can get is the particle's position. Recall, a quantum particle does not have a classical trajectory. Rather, it's described by a probability distribution. The rule is simple. The probability density at a point x is the square of the magnitude of the wave function at that location. So a large value of psi of x means a higher chance of finding the particle there. And if you integrate psi squared over a region, you get the probability of finding the particle in that region. Now take a look at the corkscrew image. This represents a one-dimensional state. At each position x along the line is a complex number, shown here as an arrow, extending from the center line out to the helix. In this example, the magnitude is the same everywhere, so the probability is uniform. The length of this vector is the same as the length of all the other vectors along the line. There's a vector at every point along the x-axis. That's what the helix represents, but I've only sampled a few of the vectors, so you can visualize this more clearly. In this example, because the vectors all have the same length, the particle is equally likely to be found anywhere along the x-axis. The angle the arrow makes is what we call the phase, and in this example, it wraps around the axis. The phase is important for interference, but it doesn't affect the single point probability. AcePhysics.org, Math and Physics Tutoring with Dr. Hudis. In this animation, I add two plane waves, one with plus k shown in the upper left, and one with minus k shown in the upper right, where k is the wave number. To make this concept clear, I plot each complex exponential plane wave, also referred to as a corkscrew, in two different views. These two waves in the upper left and right are represented using 12 complex numbers. There are an infinitely many points along the x-axis, but I sample each corkscrew wave at 12 points just to help you visualize it. X equals 0, which corresponds to the complex number at this point. X equals 0.5, 1.5, 2.5, 3.5, all the way up to x equals 10. At this location here. Each little circle represents the wave function at one position in space. The arrow inside the circle is a complex number. This is the imaginary axis and the real axis. This is the imaginary axis, this is the real axis, and this is the x-axis. The direction of the arrow shows the phase, and the length of the arrow shows the magnitude of the wave at that point. By the superposition principle, if we have two valid quantum states, any linear combination of them is also valid. The top row is the complex number e to the ikx, scaled by a constant number 1 over 2i. The middle row is the complex number e to the minus ikx, scaled by a complex number -1 over 2i. And the bottom row is the sum of the two waves. This is the familiar standing wave solution for a particle in a one-dimensional box. Looking at the bottom row, you can see the result of superposition. I'm going to change this to n equals 1. Notice the nodes here and here, where the amplitude is always 0, and the antinode, where the amplitude is the largest. So these postulates tell us that the probability density at position x is the squared magnitude of the wave function. For a standing wave, this density is not uniform. It's 0 at the nodes and maximum at the antinodes, where the wave has its biggest amplitude. The important idea is by superimposing or adding a plus k and a minus k wave, we create a standing wave with a probability pattern. I changed n to 8. Now there's 8 waves here and 8 waves here, and we have this probability distribution, where there's 0 probability of finding the particle here, and a maximum probability of finding the particle here. 0 probability here and a maximum probability here, and so on. So as you change n, the standing wave develops new nodes and antinodes, and the probability density shifts accordingly. Now let's discuss momentum. Corkscrew complex exponentials are the building blocks of quantum mechanics. Any wave function can be constructed as a weighted sum of complex exponentials with different wavelengths. This is an example of a corkscrew-shaped wave, like the one on the previous slide. It's essential to understand this function. It forms a fundamental building block of quantum mechanics. The key rule is that momentum is inversely proportional to the wavelength. Momentum, p, equals h bar times k, where k is the wave number. This means a larger wavelength corresponds to a smaller momentum, while a shorter wavelength corresponds to a larger momentum. These corkscrew-shaped, complex exponential plane waves represent one-dimensional quantum states with a constant wavelength and therefore constant momentum. A right-handed corkscrew corresponds to a positive momentum, while a left-handed corkscrew corresponds to a negative momentum. Changing the wavelength directly changes the momentum value. A wave function isn't confined to a single wavelength, just as it isn't confined to a single position. Instead, it can be formed from a mix of many wavelengths, like combining different musical notes to create a chord. Take the example of this wave shown on the right. This wave function is made from combining 3 pieces: a wave with lambda equals to 10 multiplied by 1/2, plus a wave with lambda equal to 2 multiplied by 1/4, plus a wave with lambda equal to 1.5, also multiplied by 1/4. Well, this would be the wave function representing that particle. When you measure the particle's momentum, you won't see all 3 momentum or wavelengths at once. Instead, when you make a measurement, you'll get one of the allowed momentum with a certain probability. There will be a 1/2 or 50% probability of getting a momentum corresponding to lambda equal 10. There will be a 1/4 or 25% probability of getting a momentum corresponding to lambda equal to 2, and there will also be a 25% probability corresponding to lambda equal to 1.5. The 3 probabilities or weight factors must always sum to 1 or 100%. This is very similar to our earlier discussion of position. Just as a particle's position can be expressed as a superposition of many positions, its momentum can be expressed as a linear combination of different momentum states. Finally, the wave function can have multiple wavelengths for different directions in space. A quantum wave can have different wiggle spacings or wavelengths in different directions, and those directions are independent. The left-right spacing can be one value, while the up-down spacing can be another. This is an example where the wavelength in the x direction is the same as the wavelength in the y direction, but changing one doesn't force the other to change. I'll demonstrate this by changing the wavelength in the y direction. The tighter the wiggles in a given direction, the shorter the wavelength there, and the larger the momentum in that direction. More spread out wiggles means smaller momentum. This applet lets you see how many cycles fit across the grid horizontally and vertically. And I can draw all waves, although that makes it more complicated to see. Nx and Ny control how many wavelengths fit across the grid left, right, and up, down. Let's make Nx 10. The red and blue curves are one-dimensional slices that reveal the sinusoidal pattern in each direction. Physically, the wavelength lambda x and lambda y correspond to the momentum components in the x and y directions. So a state carries a momentum vector with independent momentum in the x and y directions. This is a 2-dimensional quantum wave function. In a more general situation, a quantum mechanical state can be a superposition of many of these 2-dimensional wave functions. And of course, in general, systems are 3-dimensional, and you also have a wave function in the z direction, but that's harder to represent on the computer screen. To conclude this presentation, there will be a brief discussion about Hermitian operators, which were discussed in Postulate 2. In quantum mechanics, one of the key quantities we can measure about a particle is its momentum. If you have the wave function drawn in space, you might imagine taking a ruler and measuring the wavelength of its oscillations. The wavelength is directly connected to the momentum, but in the mathematical framework of quantum mechanics, we don't measure with a ruler. Instead, we use operators, special mathematical tools that act on the wave function and produce the measurable quantities, like the wavelength. For momentum, the operator turns out to be a derivative. This makes sense because the basic building blocks of quantum mechanics are the complex exponential wave functions. When you take a derivative of a plane wave with respect to x, you get back the same wave multiplied by a constant. That constant is proportional to kx, the momentum in the x direction. So the momentum operator in the x direction is minus IH bar d by dx. Acting on the wave function, this operator gives us the particle's momentum in the s direction. The same logic applies to the y and z directions. In this lecture series, I'm focusing on the important conceptual ideas of quantum mechanics. But if you want to go deeper into the mathematics, here are the main tools you'll need. Hermitian matrices and operators. Unitary matrices and operators. The special unitary group. Start with SU2, then move on to SUN. And finally, some group theory and Lie algebra. Thanks for joining me, and stay tuned for part 3 of the series.
AcePhysics.org. Math and Physics Tutoring with Dr. H. AcePhysics.org. Math and Physics Tutoring with Dr. Hudis.